Hello, friends. We shall continue our discussion. I will take up three-phase induction motor drive control. How to control the speed of the three-phase induction motor? We will try to look at that. We know there are different methods of controlling the three-phase induction motor, traditional methods. These we are already familiar with. Look at this. We can use an auto transformer. We can use a series reactor. We can use a series resistance, or we can have a dedicated alternator which can be controlled. In all these things, the basic concept is what? We have induction motor. To that we are giving a supply. That voltage, that AC voltage, we want to control. We control the voltage by means of auto transformer. We control the voltage by means of a series reactor or a series resistance. In all these things, the available supply is constant, we make it variable. Whereas here we have the available voltage itself as variable because we can have a separate alternator if that is possible. So there are different approaches. They have their own merits, demerits. In contrast to this, we can make use of solid state approach and then control the three-phase induction motor. That is where we come across solid state control of three-phase drive. Okay, so now that actually falls under the power electronic approach. We make use of power electronic converters. Using that, we can have the three-phase drive control, wherein we can have the supply voltage control, we can have the supply frequency control, we can have the slip power recovery, the slip power control. Varying the slip power we can control, varying the supply frequency we can control, varying the supply voltage we can control. We can have the solid state converters for this purpose. So we will look at these aspects one by one. Okay, so the solid state control of three-phase drive, solid state control of three-phase drive is what we are discussing. So first we will take the voltage control, the voltage supplied to the three-phase induction motor. It is three-phase induction motor drive control by varying supply voltage what we give to the induction motor, employing three-phase AC voltage regulator. We employ three-phase AC voltage regulator. We have already discussed in power electronics what is a voltage regulator, what is AC voltage regulator, and what is three-phase AC voltage regulator. We have already discussed about that. That we are now employing for three-phase induction motor. Okay, so the scheme, the circuit diagram looks like this. Have a look at it. The scheme looks like this. See here, we have three-phase induction motor. Its stator is there, its rotor is there, and then three-phase AC input is there. This three-phase AC input is fixed. It is fixed input, whereas we use a controller. This is the three-phase AC regulator, three-phase AC voltage regulator, and here the three-phase AC voltage regulator consists of 6 SCRs. We could have as well used 6 transistors. There are actually 3 pairs. Each pair is having two back-to-back connected or anti-parallel devices, T1, T2, T3, T4, T5, T6, and these SCRs are given the firing pulses using a controller. Controller decides the firing angle depending on the speed of the motor expected. So look at the scheme again. We have three-phase AC fixed, three-phase AC regulator, which converts fixed AC into variable three-phase AC. Three-phase AC variable. So here we have three-phase AC variable we get. When we feed that to the induction motor, the voltage to the induction motor will change and its speed will change. That is the basic principle of this approach. Look at this, the same thing put in a very compact way. Fixed three-phase AC converted to variable three-phase AC, the voltage varying with three-phase AC regulator, fed to three-phase induction motor, changing the speed. So this is the schematic, this is the circuit diagram. The circuit consists of three-phase voltage regulator with three pairs of SCRs, each pair with two anti-parallel back-to-back connected SCRs. The back-to-back connected SCRs are required because it is AC that is involved here. We need to have forward as well as backward conduction. Both the polarities are required. Both the directions of current flow are required. Okay. Next. So this method, what is the working then? The working of this, here I told it consists of three-phase AC regulator consisting of three pairs of anti-parallel connected switches. Each pair corresponds to each phase. Three phases, three pairs. These switches are operated with pre-decided value of alpha. As a result, the AC voltage gets chopping, cut. Because of this, the three-phase AC voltage regulator is also called as three-phase AC chopper, because we chop the voltage, cut the voltage, select a part of it. Part is selected as output, hence the effective output voltage becomes controllable depending on the instant at which you chop. Nothing but the value of alpha, the effective output voltage will change. Okay, so now the typical waveforms will look like this. Look at this waveform, very familiar waveform. I will show one phase and the same happening will be true with the other two phases also. Let us see for the R phase. R phase voltage is shown here. It is sinusoidal, and in R phase we have two SCRs, T1 and T2. We trigger them with a delay alpha, like this, and when we trigger T1, corresponding supply voltage is positive. T1 starts conducting, so I will get the output voltage starting from alpha till alpha from 0, no voltage, because T1 not conducting because the triggering pulse was not given. When it starts conducting, the output voltage we get will be like this, which is actually this input voltage. When the SCR T1 conducts, whatever supply voltage is there will appear as the output. The input will appear as the output. So what I get here is the same as this, starting from the instant this device starts conducting. More accurately speaking, this voltage will be slightly less than this by an amount equal to drop across this device. Hence, with an approximation, we can say this output voltage, what I am showing here, this output voltage is the same as this approximately. Exactly speaking, it is slightly less than this to the extent of voltage drop across the conducting SCR. Now, at this point, the supply goes negative. When the supply goes negative, obviously the corresponding SCR should have turned off. But this being the motor load, there will be inductive effect. Hence, depending on the effect of inductance, the conduction will continue even beyond pi. After that, that SCR will stop conduction. That means here T1 conducts from this to this point. Next, we will trigger T2 at a symmetrical position with firing angle alpha, and we get the output voltage because of T2, which is nothing but this supply voltage appearing across the motor, which is due to T2, and this and then this both are similar. And if we see this waveform, positive, negative, negative, it is still alternating, but it is chopped here, it is chopped here. As a result, instead of getting the full input voltage, we are getting a part of it, so the output is AC, but the magnitude is less. This magnitude I can change by changing this alpha, chopping it earlier or chopping it later. Chopping it earlier will make the voltage more, chopping it later will make the voltage less, which means by changing alpha we can change the effective output voltage, RMS voltage. So chopping, selecting a part, controlling alpha leads to variable voltage. Basic principle of chopper, AC chopper. So now this is done even for the other two phases also. As a result, the effective voltage given to the induction motor will change. Something that would have happened if we would have used a transformer, the same thing happens here. Now, instead of two SCRs, we can use a single track also. We know that track is bidirectional, so we can manage the function of two anti-parallel connected SCRs with the help of one track. Looks simple, na? But tracks have some issues. One is their capacity is less, for big motors cannot be employed. Second is they normally have the problem of asymmetrical triggering. That means this point and this point will not be symmetrical. As it is, due to chopping, the output will not be purely sinusoidal, it's already having some harmonics. In addition to that, if this is not symmetrical, the total harmonic content will be still more. That becomes a big problem. So because of this increased harmonics, it starts creating a disturbance in the motor. Typically, if it were to be something like a fan, it starts making that humming noise. Okay, that's why normally tracks are not employed for big power applications. Otherwise, track can also be employed. So one phase waveform I have shown, the same thing is valid for the other two phases also. Now when the motor voltage is changing like this, it will result in the change in the speed. How does that happen? Look here. The omega T characteristics of the motor, three-phase induction motor. So I have shown torque, I have shown the speed, omega T plane. On this I have shown the omega T characteristics of the motor. The omega T characteristics of the motor for different voltages will be different. As the voltage becomes less, the characteristic also will become lesser in magnitude as shown here. Please observe the omega T characteristic for V1 voltage is this. Omega T characteristic for V2 voltage is this. Omega T characteristic for V3 voltage is this. Are you able to see that? Wherein V1 is more than V2 is more than V3 more than V4. That is the relation. Now, that is the motor characteristic. We are having a motor load. The load is having this characteristic. Are you able to see that? Now, if the motor voltage is V1, the motor characteristic is this, and the load characteristic being this, the required torque of the motor is given by the motor at this point. That is why the intersection of the two will give me the operating point. Hence, the point P1 becomes the operating point. Obviously, corresponding to P1, you can see here the speed is omega m1. So, when the voltage is V1, the motor will be operating at a speed omega m1. Okay, good. Now, if the voltage of the motor is reduced, then let us say we have gone to V2. When it has become V2, the motor characteristic will be like this, and the load characteristic will intersect the motor characteristic at point P2. Obviously, the motor will operate at point P2, which corresponds to the speed omega m2. That means when the voltage is reduced from V1 to V2, the speed will reduce from omega m1 to omega m2. What we have realized? We have realized a decrease in the speed. And how we could do this? We could do this by changing V1 to V2. How we could change V1 to V2? Instead of operating V1 at a firing angle alpha 1, we operate the regulator with a firing angle alpha 2. Obviously, the voltage will become V2. Now, if I still reduce the voltage from V2 to V3 by making the firing angle alpha 3, then the characteristic of the motor will be this, and the operating point will be P3, thereby giving me a speed omega m3, which is still less than omega m2. That means by changing alpha, hence changing the voltage, I can change the speed. That's what we mean by control. Am I right? Good. This is the whole thing that goes on there in the three-phase voltage regulator based three-phase induction motor control. There is something very interesting here. Look at this. This is the same statement as I have made. Change in alpha, change in the voltage, change in the speed. But you can see here, when omega t characteristic is keenly observed, as alpha is increased, the generated torque reduces. For this generated torque is this, for this characteristic it is less, for this characteristic it is less. So, as the value of alpha is changed, the voltage changes, generated torque reduces, the operating point gets shifted as per the load characteristic, thus changing the speed. This is what we can observe here. And imagining that continuing like this will give me more speed. If I continue that process, I will have a problem. What is that? Alpha cannot be made too high. Anticipating smaller speeds. Speed is decreasing na. By increasing alpha, I cannot extend it too much, because when I make alpha too much, the voltage will be so less. The voltage will be so less. Look at this. I have made alpha so high, alpha 4, making voltage V4 so less that even the maximum torque generated by the motor is lesser than the minimum torque expected by the load. What does that mean? The motor is not able to drive the load at all. The motor stops. The torque is maximum torque is less than the minimum load expected torque. Motor will not run. That means I cannot make the speed too less, because I cannot make the voltage too less. Making the voltage too less might result in the maximum torque itself less than the minimum torque expected by the load. So, the very peak torque itself will be less than the minimum torque required by load. This results in, because of this, what will happen? I cannot have the speed range too wide. I will have a speed range very small speed range. It results in a limited speed range. That is the major demerit of this method. The method wherein we are using three-phase AC voltage controller. Is it okay? So this method, then what are the merits? It's a very simple method. Simple, and cost is less because of that simplicity, and very easy to implement. Change alpha, voltage will change, speed will change. But the demerit is the speed range is limited because it is a function of torque. And another important thing is, because it is a chopping principle that is employed, harmonic generation is very high. That's why the performance of the motor gets deteriorated. It becomes poor. Heating will be more, overheating will be there. We need to do something else to reduce the harmonics and make the waveform as nearer to sinusoidal as possible. Okay, so now what are the applications? This is a very simple method of control speed. So it is suitable in such situations wherein torque need not remain constant. Please register that in mind. Suitable for the applications wherein torque need not remain constant, like fans, pumps, etc. Also suitable for such applications wherein the speed range required is very less, not a wide speed range required. Typically for fans, pumps, very typical applications. Okay, so in such applications we make use of the stator voltage control using three-phase AC voltage regulator. Okay, so we shall stop there. Next class we will continue.